problem as finding global minimum. And so the way you go is initiate your state, which consists of red balls that are stochastically moving on the landscape. And you're trying to cool down the system, meaning it undergoes stochastic motion, and you want to reduce stochasticity gradually. Or in other words, you want to gradually cool down the system. Your final aim is to condense it in the global minimum. So you want to decrease temperature as fast as possible in order for the runtime of the algorithm to be small. But also, if you do it too fast, then you risk ending up trapped in a local minimum. So you really want to avoid this. And there comes the question of scheduling, which is really a shared problem in all the optimization protocols. Is in this example, how fast and when you can cool down faster, when you have to wait and be more accurate. It generalizes to a very similar approach, but just in the quantum universe, where instead of formulating a problem in the energy landscape, you formulate it now in a Hamiltonian. And it's kind of the same. So you now will have a solution as a ground state of H problem. And well, in general, distilling a ground state of big Hamiltonian is hard. So people came up with a strategy, which is to start with a simpler Hamiltonian H0, where it's easy to prepare ground state, and then progressively change this Hamiltonian to H problem with the parameter S that varies from 0 to 1. And so you can see that H of t starts with H0 and it goes to H problem progressively. So while this evolution goes, the spectrum of H of t Hamiltonian, which I show here, lambda g is the ground state, lambda e is the next excited state, it will evolve. We want to initiate in the ground state of H0, and then we want to keep track of the ground state. In this way, we will keep track of solutions throughout, and then when we finally evolve to H problem, we will get the solution. I think with the classical energy landscape, the analogy is that if you have a well and you spill water in it, and you want to smoothly change the landscape, in order for water not to spill out, you have to do it slowly. And it turns out that the most dangerous region in an approach like this is where the two eigenvalues come close together. Because then your state can jump from ground to excited, and then you will lose the solution. And so in this region, you have to steer parameter S slower, have to evolve slowly. Let's see it closely. And so there is a theorem that says how slowly you have to evolve. And it's an adiabatic theorem that says you can steer S as fast as delta squared, where delta is the space between the two eigenvalues. Now this gives already a first upper bound on the runtime of the algorithm. Can be upper bounded with delta min. It's a minimal distance between eigenvalues throughout the evolution. It's called spectral gap. However, this prediction is a guarantee, but it's a very pessimistic guarantee. For hard problems, the spectral gap becomes exponentially small very fast, and it's not a very structural insight on what's going on. On the other hand, there is also a more new approach, which is called xeno-dragging. It's roughly the same thing, it's just that now the evolution is not Hamiltonian, but people use measurements. So both strategies have a common point, which is spectral gap. This is the bottleneck of the algorithm. When two spectral lines become close, you have to steer slower, and you really want to understand when you can progress fast and when you should get slower and slower. While characterization of convergence for quantum annealing is extensively studied, we will focus on one for the xeno-dragging in this work. And so just to overview the problems, spectral gap prediction is very pessimistic. So because it uses the structure of the problem. So you get a prediction that works, but it's just too slow. And also is hard to extract it analytically. You have a problem, it's already hard to get spectral-gap. So for a KSAT in this work with the Zeno-Dragon approach, we want to refine this tool that by the end of this talk will give convergence rates much higher than ones predicted by spectral-gap, and probably higher. Okay, so this is what it will be about. I'll start with introducing the problem. So KSAT is complete. It basically consists of clauses which are connected by logical AND, and inside the clauses variables are connected by OR. And the problem is to find a bit string that satisfies this. I'll start with a simple example which looks like this, and I'll already give a general strategy that we'll use to solve such problems. So, for example, if you look at clause 1, there are many assignments that satisfy it, such as true, true. However, there is only one that violates it. So for each clause, we can see what violates each. So false, true violates the first clause. And then the strategy of solving is just to look at violations clause by clause, and then kick them out. Then you get the final solution. You start with all the possibilities, you look at violations, you throw them away, you get the solution. So this generalizes. And we now, in the general case, will assign to each clause a projector to a violation subspace. So in quantum language, it's orthogonal to solution subspace of the clause. And so the strategy will be to start with a homogeneous superposition of all the bit strings, and then just project out everything that violates. That's it. However, if you use this straightforward manner, you get a probability amplitude in the output that scales badly, because there is only, say, one or constant solutions and 2 to the power n possibilities. So you really need to project out violations slowly, gradually, progressively. Okay? So already at this point, I'll introduce this parameter theta, which in the annealing example, in the very beginning corresponded to S. This was parameter to modify from H0 to H problem. Now it will have a different role. So role of theta now is it will define what's logical truth and false. And it will define, well, at this point I think it's just important to understand the property. So when theta is equal to 0, none of the states will violate. Everything will be true, no violations. And when we progressively steer theta to pi over 2, then we converge to the ground truth. Projectors become the ground truth violation projectors. So we just do it gradually. And are there questions here? I think it's a confusing part. So instead of projecting out violations right away, we just build up violation projector smoothly. Well, the way to do it is it's called BZF. We want to run it on quantum computers, so we want to encode the logic on the blocks here. So each variable will correspond to a qubit, and we will encode state true as this. I'll keep it visual. And because quantum measurement can differentiate between theta and orthogonal to theta, it will be also handy to include this state, and the same for false. This is the definition for logic. And it's important at this point to just see that at theta equal to 0, logical truth and false that we defined are indistinguishable. This is the origin of why at theta equal to 0 there are no violations. Everything satisfies. Then we progressively increase theta so that in the end only solution doesn't violate. Okay, so well for now it's just definition of truth and false, and we're ready to come to the strategy of solving KSAT that I showed in a simple example. We introduce violation projectors, PI, and we will projecting out. So we will penalize this projector Q, the operator Q, which is just some closures. I think it's good to show an example of how you construct one. So if you want to construct projector in a subspace orthogonal to solution of the first clause, you take on the variable 1 orthogonal to true, then orthogonal to true on the second one, and orthogonal to false on the third one. So in this way you can construct these projectors, and I'm already ready to introduce the dynamics. It will look like this. So what it does is it dissipates out parts of rho that are in the violation subspace and the coherences. We will start from a homogeneous superposition of all the bit strings, which is plus n, and we will set up this continuous dynamics that converges to PS of theta all the time. So PS of theta is a solution at angle theta. Violations depend on theta, so because we define logic dependent on theta, and so solutions also. Okay, so before I show how it looks visually, to give more intuition, and if there are questions. Okay, I think I won't drink water at this point. I think it's better to give a visual intuition first. So we start the algorithm with the homogeneous superposition, all the possible bit strings, which corresponds to density matrix, which is like this, which is homogeneously distributed. And always PS of theta, which corresponds to solution at angle theta, is a bit ahead of the state. So on each step you want the state to converge to the solution at angle theta, and then when you're close enough, you steer theta angle further. So you progressively steer theta to pi over 2, and PS of theta progressively becomes closer and closer to the ground truth solution. And at each step you kind of project the state rho of t to the PS of theta as close as you can. So when finally we reach theta equal pi over 2, we hope to find a solution, and we want to find a solution with the biggest fidelity possible and to have a plausible runtime. And the question here is the same as I stated in the very beginning. It's the same cornerstone as how you schedule theta of t. So how fast you can rotate theta, where you have to rotate it slowly, where you can speed up and it's easy. And before I overview our results, I want to start with the state of the art. So actually, because the dynamics can be viewed as a linear dynamical system, it's characterized by, turns out it's characterized by this operator Q, the violation operator. And if you want to see how fast the algorithm converges, how fast you kill coherences and violations and approach solution, it's just enough to see how fast Q kills coherences. So density matrix can always be separated to a subspace that is solutions, that is orthogonal to solutions, and some coherences between them. You look at this object that describes how fast Q kills coherences. This is the rate at which algorithm converges. this is ground truth. This is exact. Now the problems with that is Hilbert space on which rho coherence lives is exponentially big in n. It is absolutely unapproachable to write it down with n. So people had to come up with something that will nevertheless analyze the convergence, and so they did. This is why the spectral gap. So spectral gap is a minimal non-zero eigenvalue of Q, which lower bounds the rate at which it converges. It's the only general way to understand something about convergence. Already hard again because spectral gap is non-trivial to extract. You have to diagonalize huge metrics. So for k-set we want instead of keeping track of the full Hilbert space of coherence, to get some reduced model that would be valid and would simplify this object to analyze for convergence. Okay? So instead of keeping track of this huge guy, which is exponential in n, we will just have a model which consists of two angles. One is angle theta, as always, and the second is, remember the visual representation where the state gets dragged towards the solution. So how far behind the state lags is encoded in angle phi. So basically by two angles, we'll parameterize it. And well, of course, it's an approximation, so it will come with some error. And we will be interested in finding the expression for phi and checking if it's actually valid, this model. So if the error is small enough, and if it scales with n, because maybe the method explodes. And then if it's valid, we could just analyze two-angle parameterization for convergence instead of the full Hilbert space. Right? So I had to sacrifice all the math. Instead, I will just try to give an intuition of the result. But basically, under the main equation of dynamics, we were able to achieve a thing which looks like this. So it tells you how fast phi converges to 0. I mean, it actually never converges to 0, it exponentially approaches. The convergence becomes slower when you are moving close to solution. So, it's an expectation value of the same operator, e to the minus kappa t over 2q, as before, but in a different space. So now it's in a space, it's in the state psi s1 of theta, which I didn't introduce. This is a new object, and this is what we call shell. So if you have a solution which corresponds to a bit string, its shell is just you take a superposition of states one bit flip away from it. Like this. So it turns out that this really carries the dissipating flux, and it carries information about convergence. Okay, I'll rewrite it in terms of trace so that it's closer to an expression given the state of art. As I said, it's an expectation value. But remember, we also wanted to know if the error is small, so otherwise it doesn't make sense. Right? And so we also have an expression for relative error. Relative means it's an absolute over an important part of the state we want to keep track of. We want this to be small. And so it turns out that it scales as a standard deviation of the same operator. And what's important is it can be upper bounded, very strictly upper bounded by phi over phi 0. So if you converge to something small enough, relative error will be small. And also, I don't show it here, but you can see that one has to converge at least to square root of a 1 over n in terms for the algorithm to converge. So this thing, it actually always gets smaller with n. When n grows, it gets smaller and smaller. So relative error is much smaller than 1 for big n. So the model gives an close to in the limit, it gives an exact result actually. And very fast it gets reliable result. Alright, so we will talk about this result right now. Do you have questions at this point? I think it's a lot of notation, so I can re-explain something.
I have a question. Just the use of theta here is to remain in the adiabatic kind of computation, or not exactly?
So, yeah, thank you. So I had to precise that theta is basically an angle at which the solution is at the moment. And then you have your state, which lags a bit behind, and you want to see how fast it converges to the solution at theta. The solution depends on theta. And you want to do it indeed in an adiabatic way. You want to move slowly so that you don't lose the solution. But I didn't explain why, I just immediately. Okay. I think it's not that important here. Okay, so how much time do I have? Roughly?
4 minutes.
Okay. After you raised your hand, I think I won't spend much time on the statistical physics interpretation. I find it interesting. You can ask me after if you want. But basically just rewriting the... Okay, so I want here to draw your attention to this trace. If you want to extract from this formula rate at which phi converges, I introduce beta, which is an effective dissipation time, is step at 0, 2. And this is what you can get. This rate, which is predicted by our effective model. And you can draw an analogy to statistical physics. Well, I will just say here that you can think of this result as in the low temperature regime, so when you're close to the solution, which you want when the problem is hard, the main dissipative flux is carried by manifold which is one defect away from the ground state. This is really where the slow yet important dynamics kicks in. You want to account for this. Okay. Well, I want to mainly compare it to the existing result. Now, before people had gamma exact, which is given by a guy which has row coherences, and row coherence is exponentially big, so it gets very fast. It gets impossible to simulate, and it's also hard to do analytics on that. On the other hand, we provide a formula which converges to exact solution and rows for hard problems. It doesn't matter, any problem. We have a guy that is polynomial. So this is a shell of solution. Okay, so we call it free energy because of the statistical physics connection that we found. And I want to give you now a comparison plot between the three. So this is a predicted rate versus theta. So I want to draw your attention that the hardest region for the algorithm is near theta equal to 0. When theta is small, violation projectors are non-orthogonal, and it gets exponentially more time to converge to a null space. So, okay, just remember that near theta equal to 0 is the most important part to predict. You actually want to just schedule there. It's enough. Okay, so in solid line is a ground truth. So it's given by the gamma exact. This is hard to compute. It took me ages to get the simulation. In the dashed line right above, there is, if you can see it, there is our prediction. So it predicts well, and actually near theta is equal to 0, it predicts exponentially well. Exponentially better than the prediction by the gap. So gap is the usual thing, usual way to predict things. So prediction by the spectral gap is given by those dashed lines. And as n grows, it exponentially explodes. It gives exponentially far away convergence from what it is. Very pessimistic. Okay, so this concludes. We introduce a new object. And I think I'll just say a couple of words about future work. I think it's interesting to take it and attack the problems. So now that we have a different tool, one might utilize it to predict convergence rate and runtimes for the problems. And okay, still it's not an easy guy, but it gives much more access to problems that were unapproachable before, it seems. So one might utilize this to predict convergence on easy instances, and then conjecture on the instances that are hard. This is not a proof, it's conjecture. Well, and another thing which we're right now looking in, I won't talk about it, but it's a very exciting route for me, is even when you don't know the solution, because in order for all these guys, you have to know the solution in advance. If you want to think about utilizing it for solving case sets when you don't know the solution, you might, instead of taking shell of the solution, take shell of a guess state, some random guess state, and take several of them. So it seems that it carries a lot of interesting insights on how algorithms converge. And actually, just from how the guesses converge, you might guess what the answer to the problem is already. So it gives kind of new algorithm. I won't talk about it right now. It won't be either added to the work that has all the results that I presented. It will be soon in the archive. So if anybody is interested, we can see it very soon. In this, I want to thank you, and if there are questions, I'll be happy to answer.